Good, excellent. Did anybody have a go at the next one? Y equals x squared. We should know how to draw this one by now. So what do we get if we draw the graph y equals x squared? Good, exactly. Where's the vertex? Okay. So we get something that looks like that. It's not a great drawing, but it's good enough. Okay. So you must make sure it goes through the vertex is at 0, right? The vertex is 0, 0. And of course, you know it's a positive parabola because it's a positive in front of the x squared. Like we've looked at quadratics recently, right? So something like this is absolutely fine. Did anybody have a go at the next one? Y equals x cubed?
Yes.
Yeah, what does that look like? Yeah, good. Okay, so it's kind of an advancement on this thing. It's kind of advancement on this thing. With y equals like x is the highest power, it's just a straight line. We've looked at that before, it's a linear equation, right? Y equals x squared, it turns once. Y equals x cubed, how many times should it turn?
Twice.
Twice, exactly. So that's like kind of S-shaped curve. Like that. Did anybody have a go at the next ones? So we've got y equals sine x, y equals cos x, and then y equals tan x. Did anybody have a go at those? No? Okay. We'll come back to those then. We'll come back to those because that's actually part of the next thing. So we'll come back to those ones. Okay, let's have a think about this one. Y equals the square root of x. Did anybody think about this one?
It's x equals to y squared.
Aha, good. Okay, so you're seeing a relationship there.
So
Good.
it's like a parabola, but it's like.
Absolutely. Okay. So you're seeing these two things are inverses of each other. Yeah. So you're seeing x squared. That looks like that. And y equals square root of x. What's that one going to look like? Well, what we do is because they're inverses, they undo each other. Like if you square something, the reverse operation is square rooting. We say they're inverses. They undo each other. Now the inverse is always reflected in the self-inverse. So can anybody think? What would the self-inverse be? In other words, the self-inverse basically means I put the value in and I get exactly the same value out. It doesn't matter whether I put it in or out. Okay, I get the same value. Can anybody think what equation would define the self-inverse? Okay, so what I'm literally doing here is I'm thinking about functions. Now a function is simply a rule that takes an input value, does something to it, in fact that's why we call it a function, and then we get an output value on the other side. Okay? So let's suppose, for example, well, instead of writing input all the time, let's make this a little bit easier to deal with. Let's give that a letter. We'll just call it x. We can call it whatever we like, but I'm going to call it x. Okay? Any suggestions for what we should call the output?
Y.
Yeah, makes sense, right? Because y comes after x in the alphabet. Okay, you can call it whatever you like, but I'm just going to call my output y and my input x. Okay. Now, at the moment, what I'm doing is my function could be anything I like. It could be squaring, it could be timesing by 3 and adding 2, it could be whatever I like. Okay. But what I'm asking is, can I think of a function which would give me the same output as my input? In other words, I put a value in, and I'm always going to get the same output. For example, I put 3 in, and I'm going to get 3 out. I'm going to put 5 in, and I'm going to get 5 out. I put 7 in, and I'm going to put 7 out. Because obviously if I'm getting the same value in, same value which I get out as I put in, then that's going to be a self-inverse. Because an inverse would go the other way. In other words, I stick something in this end, and I get the same value out this end. Can anybody think of a function which would give me the same output as my input? What about this? y equals x. What does this literally say? My y is equal to my x. My output is equal to my input. Does that make sense? Okay. Now what would the graph y equals x look like? Yeah, exactly. The gradient is 1, the y-intercept is 0. So my y equals x would look something like this. Yeah, that's the graph y equals x. So what I'm saying is because these two things are inverses of each other, in other words, they undo each other, okay, it should just be a reflection in the line y equals x. So if I reflect y equals x squared in the line y equals x, that should give me the graph y equals the square root of x. Okay. So what would happen if I reflect this graph in the line y equals x?
Reflected on the x-axis or?
Reflects in the line y equals x.
Oh, okay. Yeah, okay, just.
It goes like this, yeah. So I get something that looks like that. Okay. So that technically is the graph y equals square root of x. Except it's not, because there's a slight condition that we need to be careful of here. The rule of a function, just by definition, says that if I put one value in, I should always get one value out. So one value in, one value out. Now have a look on this graph here at the moment, the blue graph. Okay? If I put a value in, I don't know, let's suppose I put this value. Let's suppose I put this value in here. Okay? I get two values out. Can you see that? I get this value and this value as well. Now I can't have that because that breaks my definition of a function. I like to keep things simple. One value in, one value out. So all I do is remove that. Okay, so I remove the negative portion of the graph. So technically, that's a really long way of saying the square root of x graph should just look like this. Look like that. So think of it as a parabola, which has been reflected in the line y equals x, but we remove the negative portion of the graph to hold this condition of a function, that we put one value in and one value out. Okay. Of course, you could have kept the negative portion of the graph, but just by convention, we always take positive, because we like dealing with positive.